Hi, we are from Group 6. I will be presenting about the design of a solar water heating system in a hotel in Malaysia. And I am Nurul Sa'eidah. Together with me is Mohammad Imran, Wan Nur Alya, Mohammad Zhafran, and also Mohammad Irsyad. Here are some of the presentation overview. We'll start with the introduction, literature review, methodology, results and discussion, and lastly is the conclusion. Some of the introduction of solar water heating system basically utilize the solar collectors to capture and convert the sunlight into thermal energy. And according to Malaysian Investment Development Authority (MIDA), the current usage of solar water heating in a hotel in Malaysia has been steadily increases. This is due to the government incentives that has been introduced. For example, the Green Technology Financing Scheme (GTFS) and also the tax incentives for green investment made by any personnel. For example, there is a large-scale solar water heating systems in a Langkawi Lagoon resort, in which, as a result, they managed to reduce the energy cost consumption by 30% after the implementation. The problem statement of this study is the conventional energy sources, primarily the fossil fuels such as coal, oil, and natural gases that have a substantial environmental impacts that pose a significant challenge towards the sustainability. And aside from that, the air pollution from the burning of fossil fuels have led to the health problem for human beings. Hence, the objective of this study is to design a solar water heating system for a hotel in Malaysia with a storage tank capacity of 3,000 litre. Second is to ensure the output temperature of the solar water heating system is at minimum of 60 degrees Celsius. And lastly is to accommodate the solar water heating system in a hotel with an estimated usage of 25 litre of water per person. Therefore, to achieve all of the objectives, the scope of the study is first to analyze the solar irradiance level in Malaysia to determine the feasibility and efficiency of the solar water heating system. Second is to identify and select the appropriate solar collectors that's suitable for the Malaysian climate. Third is to design the solar collector using Fusion 360 software. Fourth is to calculate the required number of solar collector to maximize the solar energy absorption. And lastly is to calculate the energy required to heat 3,000 litre of water to a minimum temperature of 60 degrees Celsius together with the input and also the output power of the solar water collector.
Now, moving on to the literature review of our study. Nowadays, the global has started a massive shift toward a more sustainable type of energy to replace the fossil fuel. Many major corporations have initiated their own initiatives to reduce their carbon output, such as Petronas with their Net Zero 2050 program. And there are 5 main types of renewable energy that have been implemented in Malaysia, such as water, geothermal and solar. But the one that stands out the most is solar energy due to the Malaysia location near the equatorial zone with an average of 5 to 7 hours of sunlight per day.
Moving on, I'll be explaining about the evolutions of solar water heating system. This journey spans over a century, marked by significant innovations and technological advancements. It starts in 1891, when the Clarence Camp of Baltimore, Maryland patented the first commercially viable solar water heater known as the Climax. This system utilized iron tubes with elliptical cross-sections to maximize the heat absorption from the sun, laying the groundwork for future developments in solar water heating technologies. Then, in early 1900s, William Bailey revolutionized the solar water heating system by separating the water storage tank from the solar heating elements. This innovative design significantly improved efficiencies and ergonomics, forming the foundations for modern solar water heaters. Next, during the early 20th century, the flat-plate solar water heaters gained popularity in the United States, especially in sunny regions like Florida and California. So these systems become widely used, showcasing the growing interest in harnessing the solar energies. However, the 1930s and 1940s saw a decline in the use of solar water heaters due to the widespread of availability of natural gas and electricity, which offered more convenient and reliable alternative for heating water. But then, the energy crisis of the 1970s reignited the interest in solar energy, leading to significant advancements in solar water heating technology. The introductions of evacuated tubes collectors with vacuum insulations greatly improved the heat retentions and efficiencies, making the solar water heaters more effective, especially in the colder climates. The heat pump system also emerged during these periods, combining the solar energy with electricity to provide a reliable source of hot water. So nowadays, advances in nanotechnology have further enhanced the efficiencies and performance of solar collectors. The developments of nanomaterials and nanostructures coatings have made solar water heating system more effective and cost competitive, driving their adoptions in the modern households and industries.
Generally, the solar water heating system is comprised of three main components, including solar collectors, which absorb solar radiation and converts it into thermal energy. Next is the storage tanks, which stores the hot water produced by solar collectors, acting as a reservoir to be used during low solar radiation levels. Lastly, heat transfer fluid transfers the heat from solar collectors into the storage tank.
Next is the type of a solar water heating system. We have two types, which is a passive and active system. So for passive system, it relies on natural convection or direct heat transfer from the sun. It also has no external energy sources, which is electricity or pump. It has two types, which is integral collector storage, which water is stored in the integrated tank with the solar collector. It heats water directly, and it is cost efficient but less efficient in colder climates. Second system is the thermosiphon system, which rely on the natural water circulation. So solar collector is placed at below the tank. It needs a steady supply of hot water. It is more efficient but require a very careful installation. So the advantages of the passive system, it is more simpler and low operational cost. It has fewer components, which lower maintenance. It's also ideal for area that has abundance of sunlight. Next is the active system. So active system uses mechanical component such as pump or controller to circulate water or heat the transfer fluid. It is more complex but more efficient than passive system. There are two types, which is direct circulation system and indirect circulation system. For direct, the water is pumped directly through the collector into the storage tank. It is effective in climates with rare freezing temperatures. For indirect circulation, it uses heat transfer fluid. So the fluid will absorb heat in the collectors and transfer to water via heat exchanger. It operates efficiently in colder climate. So the advantages of active system, it has higher efficiency, it has a better water flow and heat transfer management. It is also equipped with sensors and controllers for optimized performance.
Let's look into the solar water heater market analysis. As you can see in the figure of solar water heater market size by application, we can see that the solar water heating system market is experiencing a significant growth from 2021 until 2024, and it is projected to increase further by 2032 in the residential, commercial, also the industrial applications. This is due to the increasing awareness about the renewable energy sources and the need for sustainable energy solutions. Next, in terms of the collector type, we can see that the flat plate collector have the biggest market size of 66.5% compared to the other two, and it is expected to grow substantially over the next few years. And apart from that, the substantial growth is in the regions with high solar irradiance, which is such as the Asia Pacific, as according to the figure of Asia Pacific solar water heater market size from 2021 to 2032.
The design methodology of this solar water heating system is initiated by defining the current problem phase before reviewing the relevant information via literatures about the optimal solar water heating system. Next, the system is designed comprehensively through detailed calculations and mechanical drawings. The findings from this solar water heating system is discussed in terms of economical and environmental viability, which will be discussed further.
Moving on to the conceptual design, we offer an active indirect solar water heating system to be installed in a hotel in Malaysia. The solar collectors is used to heat up a transfer fluid, which is circulated by a pump, where the heat from this hot fluid will then be exchanged with potable water from a storage tank in a heat exchanger before being delivered for domestic usage. These are the main components in the solar water heating system, which include solar collectors, circulation pump, expansion tank, heat exchanger, hot water storage tank, and heat pumps. So you may ask, why active indirect system? So basically, this system is the most common system used in both commercial and residential buildings due to these reasons. So the first one is efficiency and reliability. Mechanical pumps in active indirect solar water heating system ensure continuous fluid circulations for efficient heat transfer and a consistent hot water supply, even with variable solar radiations. So the second one is safety and hygiene. So heat exchangers keep potable water separate from the heat transfer fluids, which is in this case propylene glycol, hence maintaining the water quality, while the expansion tank manage the pressure, enhancing the safety. The third one is adaptability and scalability. So the system's modular designs allow for easy adjustment and future expansions, fitting various building size and hot water needs. Heat pumps ensure the delivery of hot water even during low solar radiation periods. And the last one is environmental benefits. By using renewable solar energy, it reduces the fossil fuel reliance and greenhouse gas emissions. The system's efficiencies result in cost savings and a lower environmental impact, making it a sustainable hot water solution.
For the design calculations of the solar water heating systems, the left side is the required parameter, which is such as the ambient temperature, collector heat removal, transmittance, solar irradiance, and efficiency. All of these values obtained from the references, and from these values we can obtain the volumetric flow rate of the water, which is if each person consume 25 liter per day, and assuming that there will be 1,000 clients in a hotel with a 411 rooms, the volumetric flow rate is obtained, which is 2.85 to the power of -4 cubic meter per second. From the calculated volumetric flow rate, we can determine the heat absorbed by the solar collector, which is the Q input, which obtained as 12,152 joule per second. And next, by assuming that the solar water heating efficiency of 67%, we can calculate the Q output, which is the heat transferred to the storage tank, which is obtained as 8,142 watt. Next, we can also calculate the input power and also the output power, which is the input power is obtained as 4,728 watt per meter squared, and the output power is obtained as 3,168 watt per meter squared. And aside from that, to optimize the heat absorbed in the solar water heating system, we need to calculate the number of solar plate collector required, which is obtained as 58 panels in total.
Moving on to the detailed drawing, we had modeled the solar water heater based on the calculation from the previous chapter. There are 4 major parts of the system, which is the hot water storage tank with 3,000 litre of capacity to meet the usage demand, the flat plate solar collector with an effective absorption area of 2.57 meter square, the copper tube fixture to flow the heating liquid, which in our case is propylene glycol, and a water pump to operate the system. Here is the elaborated drawing of our design. The heating liquid in our case is propylene glycol was used throughout the heating and surging line. First, the liquid was transferred through the copper tube fixture to absorb all the heat from the sun. Then, the heated liquid will flow through the copper coil here that was placed inside the water tank. Heat exchanging part happened when the heated glycol heat the water until it reached an equilibrium temperature. The now cold propylene glycol then extracted from the coil by the pump, and the step was repeated over and over. There is also an auxiliary heater to heat the water using electricity in case of cloudy days where the sun radiation is not enough to heat our water. And here are some technical drawings that had been made, including the sizing, the model layout, and the exploded view of our major components. Here we can see that the absorption plate consists of 5 parts, which is the outer top glass sheet, the absorption plate with heat conductive properties, copper tubing and insulator to capture all the heat, and lastly the base cover to keep it all together.
For component selection criteria for solar collectors, we choose to use flat plate collectors for our final selections. It offers higher efficiencies, more durable, and lower heat loss. For the storage tanks, we choose to have insulated storage tank with built-in copper heat exchangers, as it offers high insulations, efficient heat transfer, durable materials, and high thermal conductivities. For the pumps, we use high efficiency collecting pump with the additions of advanced digital control system with temperature sensors, and add some electric auxiliary heaters in our solar water heating system due to the presented reasons.
These are the purchase equipment costs for high efficiency as well as low efficiency solar collectors, where flat plate collectors, heat exchangers, storage tank, centrifugal pump, control system, piping and insulation as well as auxiliary heater is considered. So according to resources, for a hotel with 100 bedroom, a total of 10 solar water heating system is required. Thus, for the high efficiency solar collectors, it amounts up into the 1,207,000. Meanwhile, for the low efficiency solar collectors, it amounts into 1,147,000 ringgit Malaysia. The difference is because in high efficiency solar collectors, only 25 flat plate collectors is utilized. Meanwhile, in low efficiency solar collectors, twice as twice as much amount of flat plate collectors is utilized due to its low efficiency. The table shows the electrical expenses of conventional water heating system, in which 4 locations in the hotels are considered, including guest room, housekeeping and maintenance, swimming pool, as well as spa and wellness facilities. So as to calculate the payback period, the initial investment for solar water heating system can be divided by conventional water heating system costs. And as for the high thermal efficiency solar plate collectors, the payback period is approximately 9 years. As well as the low thermal efficiency solar plate collectors, the payback period is also around approximately 9 years. So, since the payback period is around 9 years, it can be said that the installation of this solar water heating system is very feasible in enhancing the energy efficiency in the hotel rooms.
Next is the comparison and evaluation of the current hotel pump system and the proposed modified model. So as we can see, our proposed modified models is using active system, which has more advantages compared to the passive system in the current system. And we are using evacuated tube collected. And in terms of efficiency, we can see that the proposed model has significantly higher efficiency when compared to the current system. In terms of heat loss, it also significantly reduced due to the vacuum insulation when we compare it to the current system. And for climate suitability, we can see that our proposed model are suitable for various climate, while current system model is not suitable for freezing climate as it using passive system. And for our control system, we are using advanced digital controllers and temperature sensors, while the current system usually doesn't have any. And for reliability and durability, the proposed model has higher reliability and durability compared to the current system. And in terms of energy saving, the proposed model is significantly energy saving compared to the current system. Next is the environmental impact of the proposed solar water heating system. So first, it will have operational benefits. It reduces operational costs. It also promotes biodiversity. Second, it has a good or healthy environmental footprint, as solar energy has smaller environmental footprint compared to the fossil fuel. It also avoids habitat destruction, soil erosion, and excessive water consumption. It utilizes evacuated tube collector, which is highly efficient in circulating pump on the existing structure. On the sustainability part, it reduces dependency on the fossil fuel. It lowers carbon emission and environmental pollution. It supports global conservation efforts and biodiversity protection. Moving on to the economic analysis, the renewable energy will have a positive economic effect. First, there will be job creation, as this is a very labor-intensive industry. So there will be job in manufacturing, installation, maintenance, and services. Second, there will be energy cost saving, as it has low operating costs. And the solar power itself has dropped in cost 80% in the past decades. It also reduces energy expenses. And third one is the enhanced energy security, as we diversify our energy supply. In conclusion, our proposed models are using active indirect solar water heating system that has high efficiency, high reliability, and safety regards. It also has an environmental benefit, as it reduces reliance on the fossil fuel and lowers the greenhouse gas emission. In economic saving, it also has the potential to reduce costs up to 50% and offer significant cost saving. And it will take a payback period around 9 years. And for the impact, it will cut approximately 1.5 tons of CO2 emission annually, contributing to the sustainability and energy efficiency.